Hey everybody, it's Mr. Oliver. This is going to be the AP Physics C Mechanics Solutions to Unit 5 Free Response Question number 1. Let's go and get to it. Alright, so this first question is a pretty classic rotation question where you've got some kind of a circular object like a spool or a cylinder or a disc of some sort with some kind of a thread, and a person's holding onto the thread and you release this cylinder and it falls down. And so as it falls down, it not only has some kind of a motion translationally speaking, going straight down, it's also going to be rotating. And so we have to consider both factors when we're working through these problems. So it says the spool has a mass m, radius r. It has a rotational inertia, which is approximated about 1/2 mr squared. And also, we're assuming that this thread is stationary relative to that sphere or that cylinder. It says express your answers in terms of the mass, the radius, the height h, at which you drop it, in fundamental constants. All right, so question A says calculate the linear acceleration of the spool as it falls. So the easiest way to do this is when you start off, let's go ahead and draw a free body diagram real quick for the cylinder. So for the cylinder, you've got two forces. You've got a force of gravity that goes straight down, and there's also a tension that goes straight up, but it's tangent to that circle. And so that means it's acting at a radius of r away from the center. So as a result, what happens is it does rotate in this direction, which is counterclockwise, and it does also fall straight down. So I'm going to treat the downward direction as positive, and the reason why I do that is because that's the direction that's accelerating. All right, so once I got a free body diagram drawn, I'm going to write an equation that talks about the net force on this object. So if you'll look, there's a force of gravity that goes straight down, and we're calling that positive. And there's a tension that goes up, which would be in the negative direction, so minus tension. Now these two things combine to cause this object to have some kind of an acceleration. And so we have to set it equal to ma. Right, now there's not much use in this right now, so let's look at an equation that talks about the rotation. And so I'm going to do some of the torques for this thing, and we're going to do it about the center point. Usually you always want to do it about the center. So I'm going to put a little torque about the center. So ignoring the fact that it's moving down, let's just look at what forces actually cause it to rotate around this center point. Well, the force of gravity doesn't cause it to rotate, but the tension on the string does. And so that tension will cause it to rotate in a counterclockwise direction. So that's actually a positive direction. So that means that this tension times this radius is causing a positive torque. So tension times radius is the torque. Now, using Newton's second law, we assume that is equal to I alpha. All right. And if you remember, for things going in a rotational direction, we can replace alpha with A over R. Because if you remember, just kind of off to the side here, A is equal to R alpha. A linear acceleration is equal to R times angular acceleration. So I just rearrange and solve for, make that substitution for alpha. And then of course I is 1/2 mr squared, so I'll make that substitution right here as well, 1/2 mr squared. Okay, and so that equals tension times the radius, and all these should be capital R's, by the way, capital R, capital R, capital R. Okay, and so now all I need to do is rearrange this equation and solve for A, because A shows up over here. It's the same acceleration A. So if I do the math, well, first of all, the R's will actually cancel. And then what I'm left with is the tension is equal to 1/2 ma. All right. So actually I could do this different ways. I'm going to change what I said. I'm not going to solve for A. I'm going to plug in this expression for tension right here into my force equation. So I'll have, once again, force of gravity, which is just mg, right? So this is just mg. So I'm come down here and saying mg minus the tension, which is 1/2 MA, is equal to MA. All right. So I've got mg minus 1/2 MA equals MA. So now this I'll solve for A. And so when you do the algebra and manipulate everything around, you should get the acceleration is 2/3 of g. Right. And this is one of these setups to where if you do several of them, do them for a cylinder, maybe a ring or a hollow sphere or a solid sphere, you'll see that these accelerations are always some kind of a fixed ratio of g. It just so happens for the cylinder, it's 2/3 of g. And if you maybe spend a little time, you could go in and find out what all the different accelerations would be for the different cylindrical or round shapes. And it'd be helpful. All right, guys, this part was worth plus 4 points. Now, question B says calculate the angular velocity of the spool just before it strikes the floor. All right, so what I'm going to do is I'm going to calculate the linear velocity just before it hits the floor, and then I'll make a translation or a conversion into angular velocity because I know that V is equal to R omega. So if I can find V, I just got to divide by R to get omega. So for part B, let's find the linear velocity and then make that conversion. So this object is being dropped from rest, and so it does have an acceleration down. So it's a constant acceleration. It's 2/3 of g. So I'm going to use a kinematic equation. V squared is equal to V naught squared plus 2a delta y. Well, my initial velocity is 0. It's easy enough. My acceleration is 2/3 of g, and my change in vertical position is just the height. And so 2 times 2 is 4, so we get 4/3 gh. That's going to equal to v squared, and of course v is equal to the square root of 4/3 gh. All right, so that's how fast it'll be moving linearly, but the question asks for how fast is it moving in a radial direction. So since v is equal to r omega, omega is v over r. So in this sense, omega is going to be square root of 4/3 gh divided by the radius. And that question is worth plus 3. All right, now part C says at time t equals 0, the spinning spool lands on the floor without bouncing and comes free from the thread. It continues to spin but slips on the floor's surface while doing so. So it lands and hits, and it kind of spins out a little bit before friction kind of takes over and it's going to start to move. So it's like a little, it's skidding out, it's like spinning, and then it takes off. Okay, so this is basically a yo-yo, and there's a little yo-yo trick called walking the dog. And so one of the things is that you can make the yo-yo go down, and it'll spin and rotate, and you'll see that yo-yo kind of spin, and it'll kind of take off. All right, so that's what they're doing. We want to calculate the angular velocity of the spool as a function of time. So how do we do this? Well, at the time that it hits the ground, we've got an object that is rotating with an angular speed omega. Well, that's the omega speed, the initial speed that we found, or the speed that we found whenever it hits the ground. So that's the same expression. But because there's friction down here, there's some friction on the ground. As it spins this way, the friction is going to slow that rotation down. And so it has to have a counter torque in the opposite direction. And so that means that the friction is actually to the left, right? And so what that does is it causes an angular acceleration, a deceleration on that rotation. So what we want to do is we want to find omega as a function of time. Well, because I know that friction is a constant force, it doesn't change over time, I can just use kinematics. So I'm just going to use omega is equal to omega naught plus alpha t. All right, so I know what omega naught is. It's this thing. Time is just my variable, so all I need to do is find alpha. So how do I find alpha? Well, in this situation, we've got a torque caused by the friction, right here. So I'll use torque is equal to I alpha. My torque is this friction times this radius. Okay. F, lowercase f, sorry. And that equals I alpha. So therefore alpha is the friction times the radius divided by I. Now the friction is mu times my normal force. And my normal force is just going to be the same as the force of gravity. So my friction term right here is mu mg times my radius r divided by my rotational inertia, which we found earlier in the problem statement, is 1/2 mr squared. And so we can kind of reduce this down a little bit. We'll lose this r up here, get rid of that. R on the bottom, we'll cancel one of the m's. And this 1/2 we can kind of turn upside down to put the 2 on top. And so therefore our alpha, our angular acceleration, is 2 mu times g divided by r. Okay. Now because it's causing it to decelerate, in fact if you look at the direction of that acceleration, that's in a clockwise direction, that makes this value negative. So we're going to make this a negative value for the acceleration. So now all I need to do is substitute in for omega naught, alpha, and of course t is the variable. So omega as a function of time is equal to square root of 4/3 gh over r minus 2 mu g over r times the time. And that is your expression for the angular speed while it's sitting here on the ground spinning around. Right? This is worth plus 4 points. All right, next question. Part D says calculate the horizontal speed of the spool as a function of time, assuming horizontal speed is 0 at time t equals 0. So horizontal speed, how are we going to do that? Well, if you look at it, that as this disk is rotating, for part D, there's only really one force that can make it go forward, right? So if we go back to the free body diagram we had before, yeah, there's a force of gravity going down and a normal force, but there's only one horizontal force. And it turns out that that horizontal force is the friction. And it seems kind of counterintuitive, but even though it's spinning and rotating and there's all other stuff, that's the only force that could possibly make it go forward. So I'm going to use F equals ma, where the force is my frictional force, and solve this for A. Well, that's what it's asking for, or we're going to find the velocity, so we need to find the acceleration. So frictional force is just mu times the normal force, which is ma. Normal force is mg equals ma. So therefore A is just my coefficient of friction times g. Mass cancels. Right, so then I'm going to take this equation, and because that's a constant value, even though this is a mu term, it's still a constant, I can use kinematics. So V is equal to V naught plus AT. So therefore V is equal to mu g times t. Now, is it still spinning at this point? Yeah, it is. It's still spinning. But until we get to a certain point, and the next question kind of talks about that, this thing will start to move to the left because of that frictional force. All right. Part E. Part E asks, at what time does slipping between the spool and the floor cease? Well, the only way for me to figure that out is I need to understand that slipping occurs, or non-slip actually, non-slip conditions. There's one key fact, not slip, that we can count on, and that is that the velocity of the center of mass is equal to the radius of that circle times the angular speed of that circle. That's the key term that you need to know to figure out when it stops slipping. All right, this is a fact. So what I need to do is I need to use my equation from part C right here and find out what time it occurs at that omega is equal to my velocity of my center of mass, in other words, my linear velocity, which is right here, divided by the radius. Okay, so the condition for the angular speed is that mu gt divided by r is the speed at which it begins to not slip. So let's take the equation from part C for the velocity and this from part E, or for this part, and substitute them in and solve for time. So it's a little bit of algebra. So we'll have, here's our equation that we're starting with right here. Omega t is equal to the square root of 4/3 gh over r minus 2 mu g over r times time. So I'm going to set this equal to this. So we'll have mu gt over r is equal to the square root 4/3 gh over r minus 2 mu g over r times time. Right, so immediately you can see that it gets easier because the r terms cancel, right? So all these r terms cancel, and so we have mu gt is equal to root 4/3 gh minus 2 mu gt. And so if I want to solve for time, I got to move this to the left hand side. So we'll have 3 mu gt is equal to the root of 4/3 gh. And I just got to divide by 3 mu g. 3 mu g. And so that means our solution for the time at which it no longer slips is root 4/3 gh divided by 3 mu g. And guys, I know some people are kind of annoyed with having this kind of a root on top of a fraction. If you want to kind of clean it up, you can. It's not really necessary. The end result of that was rationalizing the function or whatever is going to be root 4h over 27 mu squared g. I don't really like that, but that's technically reduced to its simplest form. Right? And guys, this solution is actually only worth plus 2 points. The previous one was worth plus 2 as well. All right. Now part F, I actually chose to put in there because it's from another question, but I think it's a useful skill. So part F talks about, they cut a little wedge out of it, and what we want to do is we want to find out what the rotational inertia of that little wedge is. And they tell us that its density changes as a function of the radius, right? So 25 over big R squared, this is just a constant term. Mass M is the mass, and little r is the radius of r measured outwards away from the center. All right, now I highlighted here, it didn't do this in the original problem, but I said it's a very narrow wedge. So what does that mean? If it's very narrow, you can essentially treat this thing as a purely linear, like a long slender rod. So like if here's the axis of rotation, the fact that this thing is really narrow, you treat this more as a long slender rod instead of like a triangle shape, right? So first thing I need to know is that the overall length of this is the radius of r, capital R. It also has a mass. It says that's a mass of m, and it also has linear density, which is m times little r over 25 big R squared. So that's the linear density. So what I need to know is I want to calculate the rotational inertia of this rod. So if you go back to our calculus form for rotational inertia, I is the integral of r squared dm. Okay, R is the variable, dm is the thing that I gotta change. So the mass actually changes as the length goes along. So if I were to choose some tiny little piece, dm, I need to know what is that. And I'm going to integrate it between the beginning point all the way to the end of the rod. So my limits are 0 to capital R. So what is dm? Well, if you remember from previously, it's lambda dr. Okay, we did that in class. So the lambda in this case is not just a constant, it's actually a function. So dm is equal to mr over 25 capital R squared dr. So that term for dm is what I'm going to substitute in right here for my integral. So we're integrating from 0 to r squared dm, which is now mr over 25 capital R squared dr. Okay. The constant terms I can pull out of this, so I'll have the integral of the mass divided by 25r squared, where r once again is capitalized, integrating from 0 to capital R of r squared times r, so that's r cubed now, dr. Now this is a simple enough integral. We'll still have our constants out front, 25r squared. The integral of r to the third power is 1/4 little r to the fourth. And we're going to evaluate that between 0 and capital R. The 0 term we can ignore and just substitute in capital R for the little r. So we're going to have m divided by 25r squared times 1/4 capital R to the fourth, which we then can reduce a little bit. This r squared on the bottom goes away. The one on top changes to 2, and 25 times 4 is 100. So our final solution is 1/100th m capital R squared. All right, and that is the derived expression for the rotational inertia of that wedge. All right, and that was worth plus 3 points on the original test. It wouldn't necessarily apply here, but that's how much that points was worth. Now the second part says derive an expression for the rotational inertia of the modified disk. In other words, the disk after the narrow wedge is cut out. So here, this is pretty easy, because if I have a disk that was originally solid and it had rotational inertia which was 1/2 mr squared, that was stated in the problem, and I cut out a little sliver out of it that removed some inertia, removed some mass out of it, which was I wedge, we'll call it I wedge, is 1/100th mr squared, then that means for this shape that doesn't have the wedge in it, the rotational inertia is just going to be the difference between these two. So my new, I'll just say my total for this entire Pac-Man shape here is going to be the disk originally minus my wedge. So 1/2 mr squared is 50/100ths minus 1/100th mr squared, and you get 49/100ths mr squared. And that concludes the solution for this free response question. Guys, if you have any other questions or issues, you need to ask me a question, just let me know. I'll be glad to help you out, and we'll see you on the next one. Bye-bye.